Hi everyone! In this video, we will learn how to create a compartmental model for a vector-borne disease, model a public health intervention, and analyze the impact of it on disease transmission dynamics. A vector-borne disease is an infectious disease transmitted by vectors, such as mosquitoes or ticks, that carry pathogens from one host to another. When modeling a vector-borne disease, it is important to not only model the state of the human population, but also the vector population and include how they interact with each other in the infectious transitions. We will begin by defining a simple SIR model for the human population. For this, we will create 3 compartments: susceptible, infected, and recovered. We will then connect them with one transition for infections and one for recoveries. Next, we will model the vector population. The vector population differs from humans in multiple ways. They not only have a much shorter overall lifespan, but once infected with a pathogen, they quickly progress to the infectious state, before dying eventually. We need to account for these differences when modeling the vector population. Due to this, we will only create 2 compartments: susceptible and infected, and leave out the recovered compartment. Both compartments are connected with an infections transition. Finally, we will also model the births and deaths of the vector population to account for their short lifespan. Now that we have our model structure set up, we need to add the actual numbers and equations. We start by specifying the initial sizes of our population. We will set the initial number of susceptible humans to 10,000, the initial number of the infected humans to 10, and the initial number of recovered humans to 0. For the vector population, we will set the initial number of susceptible vectors to 20,000 and the initial number of infected vectors to 10. We know from creating SIR models that the infectious transition is usually defined by the contact rate between individuals, the number of susceptible individuals, and the portion of infected individuals of the whole population. For a simple vector-borne disease, we can extend this concept by replacing the contact rate with the mosquito biting rate, and the portion of infected humans with the portion of infected vectors. This gives us the equation of biting rate times susceptible humans times infected vectors divided by the total number of vectors. For the vector population, the infectious transition can be defined similarly, but with the roles of humans and vectors reversed. This gives us the equation of biting rate times susceptible vectors times infected humans divided by total humans. Now we need to define variables for the total human population sizes. We do this by creating a new variable called NH and setting it as the sum of all 3 human compartments. We'll then do the same for the total vector population. Finally, we need to define the biting rate. We'll set this value to 0.4. For the human population, we'll assume an infectious period of 8 days. Additionally, we'll assume that the vector population remains constant, which means that the birth and death rate for our mosquitoes will be equal. We'll first create a variable for the mortality and set it to 0.25. Next, we'll set the deaths of our susceptible vector population as mortality times the susceptible vectors. We'll do the same for the deaths of our infected vector population. But this time, we'll use the mortality times the number of infected vectors. Next, we'll set the births of the vector population as mortality rate times the total population size. We can now simulate the model and look at our first results. When generating plots, SIRcraft automatically detects 2 different populations and generates separate plots for each of them. The parameters for humans are shown on the left, and the parameters for vectors are shown on the right. Next, we will model a vector control intervention, such as insecticide spraying, and learn how to use SIRcraft's visualizations to analyze how changing the timing of the intervention affects disease outbreak. We will model the impact of the intervention as a sharp increase in the mortality of the vector population. We start by creating a new variable, t, that represents the time at which intervention starts. We change the type to constant and set its value to 30. This variable will allow us to specify when the intervention is implemented in the simulation. We'll then change our mortality rate to depend on the timing of the intervention. More specifically, we will set the mortality rate to 0.25 before the simulation reaches time t, and to 0.5 afterward. When simulating our model again, we can see that the increased mortality rate leads to a rapid decline in new infections. To easily change the timing of the intervention, we can create a slider in the interface that allows us to adjust the value of t dynamically. This will enable us to explore different intervention scenarios more easily. SIRcraft provides a variety of tools for analyzing the timing of an intervention and its impact on the disease outbreak. Let's start with removing some of the generated plots to free up space. To visualize the timing of the intervention, we can create a vertical line on the simulation plots that indicates when the intervention is implemented. This can be done by editing the plot and adding a line to it. We then set the line type to vertical and set the x-coordinate to the constant value of t. This line will help us see the exact moment the intervention takes effect and will automatically move when we change the value of t. We can use a similar technique to see when a compartment crosses a certain threshold. For example, when the number of infected humans exceeds the number of available hospital beds. This time, we'll add a horizontal line and set its height as 2000. To highlight the peak of the simultaneous infected individuals, we can add a marker at the maximum point of the infected compartment. SIRcraft can also automatically calculate certain metrics based on the simulation results. For example, we can calculate the total number of infections over the course of the outbreak. Finally, we can organize our visualizations as we see fit by giving them names and grouping related items together with headers. Here is another possible visualization of the results. And that's it. We hope you enjoyed this video, and you can find more videos and tutorials on our YouTube page, SIRcraft.